Hello, my name is Matthias Scheffler and I am from the NOMAD laboratory in Berlin, which is hosted by the Fritz Haber Institute of the Max Planck Society. This is the first lecture of a series of 8 two-day tutorials that address the theory and computations of properties of materials from first principles. In the name of all the organizers and tutors, I'd like to express a very warm welcome. You will meet all these people during the next meetings, sessions again, and you will see that some of the organizers in fact also act as tutors, but they are not listed here twice. The series is organized as a virtual hands-on tutorial using the computer code FHI-aims. This here is the homepage of FHI-aims at FHI-aims.org. This is the highly accurate and efficient computer software evaluating the quantum mechanical electronic structure. As the 3 yellow buttons tell, the code is versatile, that is, it can handle molecules, clusters, nanostructures, surfaces, and solids. It is also precise and accurate in the sense that it deals with density functional theory and very different exchange correlation functionals, but also many body methods and quantum chemistry. And the code is scalable. This will say that it runs on laptops, but also on highest performance computers. All these aspects will be covered again in more depth during the next 8 months. If you click on the upper topic, who we are, you will see that FHI-aims is the product of a very large community, without whom this code would not exist. To everyone whose hard work made what FHI-aims is today, we are very grateful. It is a great and stimulating community. I can't read all the names, but I'm sure that some of them you will know. In fact, we are sure that this list is not complete, and we apologize for this. As soon as we learn that we missed someone, we will of course correct the oversight. We hope that in the future some of you will also contribute. Most people, however, may not develop but use the code for hot, important and urgent scientific topics. The distribution and all the infrastructure of the software is coordinated by a few people, namely the FHI-aims coordinators. The key people in terms of the main concepts are noted here in black: Volker Blum, Mariana Rossi and myself. Volker is the undisputed leader of the whole endeavor. 2 people are noted in blue: Said Bolaul and Sebastian Kokot. These are the only people who are paid from FHI-aims income, and they work full-time on the various infrastructure and duties and challenges. FHI-aims is distributed by the association MS1P, Materials Simulation from First Principles. This association has the charity non-profit status, which implies that the members of the association, that is the people noted here in black, will not get any money. All the income for FHI-aims goes into the maintenance of the infrastructure, code developments and running events like this workshop. As I said before, the code was developed mainly, though not only, for material science. Most of you have a material science background, so there's no need to explain in detail why material science is important. However, as this is the very first lecture, I have one slide here which I took some time ago from the US Materials Research Society. Advancing materials, improving the quality of life. What do I mean with this? Now, prosperity and lifestyle of our society are very much governed by achievements of condensed matter physics, chemistry and material science, because new products for the energy, environment, health, mobility, IT sectors and so on largely rely on improved or even novel materials. Knowing about the relevance of material science and also knowing how many people are working in this field, it is interesting to realize how little is actually known. Considering the about 100 atoms of the periodic table of the elements and all possibilities of mixing these atoms in all possible structures and unit cell sizes, implies that the number of all possible materials is practically infinite. This implies that it's very likely that materials exist that we don't know so far, and that have novel properties or show a performance in their function that is better than that of the materials we know to date. Or it may be that some known materials have properties that have not been recognized so far. In fact, from the practically infinite number of possible materials, we know just 250,000. Compared to infinity, this is not much. And with this respect, and with respect to the material's properties, we know very little. Here you see, we know very few elastic constants or dielectric constants and so on. The knowledge is very shallow. So there are many possibilities and needs for basic science and for new or better commercial products. So how is material science developing and where is it going? Let me briefly discuss the past and upcoming research paradigms. Maybe just a clarification. A paradigm is not just the introduction of a new method or a new concept. It is a new way of thinking. Sometimes it is argued that with a new paradigm, the previously established understanding is no longer valid. This is not true here. A new paradigm in basic research means new, important, and complementary way of thinking. Typically, science advancements go together with the availability of new methods. Indeed, this is behind the different steps which you see here. Experimental research dates back to the Stone Age, and the basic techniques of metallurgy were developed in the Copper and Bronze Age, which started about 5,000 years before the Common Era. The control of fire prompted a major experimental breakthrough. Towards the end of the 16th century, scientists began to describe physical relationships through equations. Well-known names from the early days are Tycho Brahe, Galileo Galilei, Johannes Kepler, Isaac Newton, and Gottfried Wilhelm Leibniz. The latter two, Newton and Leibniz, also developed the concept of the mathematical differential and derivatives. Thus, analytical equations became the central instruments of theoretical physics. This new way of thinking, the second paradigm, is symbolized here by the Schrödinger equation. Needless to say, the first paradigm, the empirical and experimental sciences did not become obsolete, but theoretical physics represents an important complementary methodology. Since the 1950s, electronic structure theory was advanced for materials by John Slater. The Monte Carlo method was introduced by Metropolis et al., and Alder and Wainwright and Raman introduced molecular dynamics. Hohenberg and Kohn-Sham led the foundation of density function theory in the mid-1960s. All these developments enabled computer-based studies and analysis of thermodynamics and statistical mechanics on the one hand, and of quantum mechanical properties of solids and liquids on the other hand. They define the beginning of computational material science, what is nowadays considered the third paradigm. Initially developed independently, the fields of electronic structure theory and statistical mechanics and thermodynamics are now growing together. And you will learn about this growing together in this course, when we discuss molecular dynamics and canonical methods, heat transport, to mention just some examples. Likewise, in parallel to DFT, many body techniques based on Green's functions were developed. Hedin in 1965, and are now synergistically interleaved with DFT to form the forefront of electronic structure theory, including excitations. Of course, also this will be covered in this course. Today, big data and artificial intelligence revolutionize many areas of our life, and material science is no exception. Jim Gray had probably first discussed this fourth paradigm, arguing explicitly that big data reveal correlations and dependencies that cannot be seen when studying small data sets. Let us generalize the big data concept by noting the complexity of the material science and other sciences as well. The number of potential but initially unknown descriptive parameters that characterize or identify the properties and functions of interest may be very big. Thus, the diversity and complexity of the mechanisms represents a big data issue in material science as well. A further important difference to the second paradigm is that we now accept that many materials properties, patterns and correlations in big data cannot be described in terms of a closed mathematical formulation, as they are governed by several intermingled theoretical concepts and multi-level intricate processes. As a consequence, such patterns represent and advance knowledge, but they do not necessarily reflect understanding. This is the field of nomad, and it will be addressed in the last two tutorials of this course in February and April. Today's tutorial and my remaining talk deals with the second and third paradigm. So let me start with some very basic remarks, but then we will advance. Modeling materials, properties and functions means, if you want to do it reliably, solving the many-body Schrödinger equation. This is written down here. The Hamiltonian has the components, the electron kinetic energy, the kinetic energy of the ions or nuclei, the interaction between electrons, the interaction between electrons and ions or nuclei, and the ion-ion or nuclear-nuclear interaction. This is the Hamiltonian, and the wave function coming out of it is a very complicated beast. It depends on all the positions of the electrons from R1 to Rn, typically 10 to the 23, and all the positions of the nuclei from capital R1 to capital Rm, also typically of the order of 10 to 23. The operators are known. So the kinetic energy is the momentum squared divided by the electron mass. For the ions or nuclei, we have the momentum of the nuclei divided by the mass of the nucleus, I. And then the interactions are all Coulombic. So there is the electron-electron interaction, depending on the distance between electron K and electron K prime. The ion-ion interaction, or nucleus-nucleus interaction, depends on the nuclear numbers, Zi and Zi prime, and the corresponding positions, and the electron-ion interaction. In the same way is the Coulomb interaction between ion at position I and electron at position K, summed over all electrons and all nuclei. So all these things are known. We know all the operators, we know all the interactions. We can write them down. So in principle, no open questions here, but it has been realized early on in quantum mechanics. The equation is known, but it cannot be really solved. And the reason why it cannot be solved exactly, at least not be solved, is this electron-electron interaction. If this would be simpler, we would know what to do with this. In this term here, it's a very strong interaction. That means electrons are not really independent. So the first approximation to make this solvable is the Born-Oppenheimer approximation. That means that we write down the wave function of electrons and nuclei as a sum over, if you want, a basis set, where the basis sets are the wave functions of an electronic problem, splitting off all the electronic pieces of the Hamiltonian we have seen before. That means the kinetic energy of the electrons, the electron-electron interaction, the electron-ion interaction. Using this as the basis and then summing with appropriate coefficients is no approximation. So this is in principle exact. And it also tells us here the Schrödinger equation of the electrons is determined by the positions of the atoms, by the nuclear charges, Zi, and by the total number of electrons. So this is what determines everything. This determines the Hamiltonian, and the Hamiltonian then determines our basis set, the electronic wave functions. In the Born-Oppenheimer approximation, one now introduces the following assumption. We neglect what is called the non-adiabatic coupling terms. That means terms of the order of electron mass divided by nuclear mass, which are terms in certain matrix elements. And second, from the sum, we only keep the very first one, lambda 0. In words, that means we decouple the dynamics of electrons and nuclei, or we assume that electrons follow the nuclei instantaneously. This is an approximation. It often works, but there are also some very well-known and significant limits of the Born-Oppenheimer approximation. The Born-Oppenheimer approximation does not account for correlated dynamic of ions and electrons. And we know that this happens in some cases, for example, in polaron-induced superconductivity. It also happens in the dynamical Jahn-Teller effect at defects in crystals. So this is an effect where the geometry of the crystal around defects is distorted because of the symmetry breaking, but there are several symmetry identical positions of the nuclei, and if the energy barrier between these different positions is small, the atoms are in fact not sitting in one position, but are somewhat dynamically distributed. There are some other somewhat similar phenomena in the diffusion of solids. There is known adiabaticity in molecule surface scattering, well known, and chemical reactions. And there are issues in relaxation and transport of charge carriers, electrons and holes, and so on. So we always have to keep an eye on this. If these things could happen, we have to be careful with our results. The limits can be severe, but often they are not. In the following, we will use the Born-Oppenheimer approximation. We will not go beyond that. And that means we now have to solve this electron Hamiltonian, the Schrödinger equation with this HE. How can we do this? We have made an approximation Born-Oppenheimer, but still this is a significant challenge and cannot be done exactly. Before I show how we are doing it, let me mention one other thing. The total energy has two parts. It has this part coming from the electronic Hamiltonian, E0E, and it has another part coming from the nuclear interaction. So the first thing is from DFT, as we'll discuss in a moment. The second part in the Born-Oppenheimer approximation is a classical term. It's the expectation value of the nuclear potential, which can be really evaluated with the Ewald summation technique. But then in addition, we have quantum mechanical corrections for lattice vibrations. This is the expectation value of lambda 0 with the ionic or nuclear kinetic energy. Sometimes that plays some role. It's not complicated to evaluate it, but and therefore I really just want to mention it. Here you see the total energy as a function of the lattice parameter, or the total energy divided by the number of electrons or atoms. This has a minimum. And typically you would say the minimum is where the lattice constant is. Now this curve is, however, not symmetric. It is steep on the left side because there is Pauli repulsion, very strong, and it's somewhat more weakly changing on the right side. And that means that the position of the minimum is at this point, but as atoms are not really static, but they vibrate with their 0-point vibration, their average position is here. So the total energy per atom without 0-point vibration as a function of the interatomic distance, this is what is called the Born-Oppenheimer surface. But the measured interatomic distance is the average over the position of the vibrating atoms. And that is typically slightly bigger than the Born-Oppenheimer minimum. Now, density function theory, I think, is nothing really surprising. The essence of density function theory was known already in the 1920s. We have said before, the Schrödinger equation of the electrons is determined by the atomic positions, the nuclear numbers, and the total number of electrons. Now, if we have the ground state electron density, inspection of N of R, in fact, tells us the positions of the atoms. Where the position of the atoms in material science or chemistry are the positions where the potential is infinite. The Coulombic potential is going to infinite, it has a divergence. And therefore you can clearly see this in the electron density, if you have an all-electron theory or a measurement. So the position of the atoms is visible from the density, but because of the behavior, because of this infinite divergence, you can also in fact get the nuclear charges from the electron density at the positions of the atoms. And of course, integrating the electron density means you get the total number of electrons. So inspection of the electron densities gives us all the numbers which we need to build the Hamiltonian. And that means there is an obvious algorithm. The ground state density N of R gives us the positions, the nuclear charges, and the number of electrons. Of course, that defines the many electron Schrödinger equation, and that defines the ground state energy and even everything. So there is an algorithm which tells us N of R determines the ground state energy and everything. But it's an algorithm. It's not a closed mathematical expression. In this idea, density function theory says or starts from the known variational principle of the Schrödinger equation, that if you have an expectation value of the Hamiltonian with respect to the wave function, the minimum with respect to test wave functions, the minimum of this expectation value is the total energy, the ground state total energy. And what Kronberg and Kohn have shown mathematically is that the functional n of phi, which tells phi determines the density, and we know how the functional looks like. The functional is the expectation value of the Dirac delta function at the of the electronic positions. So phi clearly determines the density. In density function theory, basically in what I've said with the algorithm already, we know that the density in fact determines the wave function. So there is a way from the density to the wave function. And that implies everywhere where I had in the top red part the wave function, I can replace this by the density. And so I can say this variation principle with respect to the wave function can be transformed into a variation principle of the density. And so the minimum of an energy functional with respect to the density is the same energy which I would get from quantum mechanics. Kronberg and Kohn, here is a picture from about 10 years ago of Walter Kohn, have done this in a very nice proof, which is called in mathematics reductio ad absurdum. So we start with the assumption, with the ansatz that we have a set of known degenerate ground state wave functions phi of an arbitrary n electron Hamiltonians. So each Hamiltonian has a different phi. From phi, I can go to the density because there is a functional which determines how I go from phi to the density. And if I have on the right a set of particle densities of non-degenerate n-electron ground states, you can draw arrows. From phi 2 I go to n2, from phi 5 I go to n5. And now what Hornberg and Kohn have done is they assume that two different wave functions, which belong to two different Hamiltonians, give the same density. This is the Ansatz, and then they use this assumption in basically standard quantum mechanics, and what they find is that this gives an absurd, clearly wrong description. So, the Ansatz, if the result is absurd, that means the Ansatz was wrong, and that of course means the concept that two different wave functions can give the same density is just wrong. Means the dashed arrow is not possible, shown by reductio ad absurdum. Thus, there is a one-to-one correspondence between the wave functions of the many-body problem and the electron density. And as we said before, the variational principle of the Schrödinger equation is transformed into the variational principle of an energy functional. We only know that there should be some type of a functional, but we don't know that. Now, Levy and Lieb, in a somewhat different way, one more concentrated on the density, the other one more concentrated on the external potential, have shown that in a more general way. Hornberg and Kohn showed that for non-degenerate situations, what Levy and Lieb did is a clear generalization for degenerate wave functions. So with the external potential, here in material science, the electron nucleus, Coulomb potential, and the concavity and continuity of the ground state energy, it means if I change the potential a little bit, if I move, for example, atoms a little bit, the energy will also change very smoothly. This gives us the variational principle from quantum mechanics can be split up in two different pieces. I can do first the minimum with respect to wave functions, but I constrain the wave functions that they give a certain density. Oops, okay. So the phi here in this straight brackets is an antisymmetric wave function of the n-electron system, restricted to the request that it leads to n of r. So I first do the minimization with a constraint, and then outside the brackets, I just do and generalize the question to any density n of r. This defines, obviously, a universal density function f of n of r, which is the blue one, which means f of n is universal because it is the expectation value of the kinetic energy of the electrons and the electron-electron interaction with respect to wave functions for the constraint, under the constraint that these wave functions, they all give the same density n of r. But of course, only one of these wave functions is the true ground state wave function. It's universal because it does not depend on the external potential. So this is a generalization and very useful for further treatments and analysis of this function f of n, which somewhat has all the information very similar to the energy function, which we have here on the top. The advantage of density function theory is very obvious if you compare to wave function theory, whereas in the Schrödinger picture, we have the expectation value of the Hamiltonian with respect to the wave function, and that means the coordinate here is not just one coordinate, is very, very high dimensional, depends on wave functions which depend on 10 to 23 variables. And doing the variation for the right wave function, we find the minimum. In density function theory, this is simplified, it's transformed into a variation with respect to the density. And again, the density only depends on x, y, and z, and for the right density, I find the same minimum. And the wave function phi 0 on the left, the density on the right are corresponding to each other, and the energies are the same. So clearly, DFT is at least conceptually a significant improvement or simplification. That is just a concept and an idea, but you cannot really use that in any practical means. The Hohenberg-Kohn-Sham ansatz of density function theory is then making this whole theory practical. So Kohn and Sham said, let us replace the original many-body problem by an independent electron problem that can be solved. So to some extent, so they basically assume that the density of the many-electron system can be approximated well enough, infinitesimally close, by the density of a known interacting system. So they write down, and you can always do this in physics at least, you think you can do this, that you say I split off now the kinetic energy of known interacting particles. So Ts of n is a kinetic energy operator or functional of known interacting particles. That means the densities which I can plug in here is the density of a known interacting system. And then I have the interaction of the electrons with the nuclei, I have the Hartree potential, and everything which I have done wrong in the previous terms, that means in the kinetic energy, is in the exchange correlation function Exc of n. With Ts, the kinetic energy of independent electrons and non-interacting electrons, Exc is the only remaining unknown in this equation. We don't know that, and I would argue it probably doesn't exist in an exact way as a functional, which you can write down in a closed mathematical form. But the challenge is to find useful approximations to this exchange correlation functional. This is the issue. The existence of a one-to-one relationship, as proven by Hohenberg and Kohn, or by Levy and Lieb, does not really imply that the exact exchange correlation functional can be written down as a closed mathematical expression. In fact, it may be just this algorithm which we mentioned before, that if you want to evaluate it, you have to go all the way from the density to the positions and charges and number of electrons to the Hamiltonian, and then you get the energy. Maybe it's just an algorithm and not really a simple functional. Approximating this algorithm by a functional, that is by a density function approximation, DFA, suffers from the severe problem that the range of validity of this functional is typically unclear. We can test the calculations by doing studies where we know experimental results or where we know quantum chemistry results. But then if we use it for something else, we are never really sure if the situation will be different. Typically, we have a feeling what materials may be similar, but there are examples where one can be pretty wrong. So Kohn and Sham have continued these thoughts in saying I have a functional which is Ts plus the interaction with the nuclei plus the Hartree plus exchange correlation functional. And as Ts is the kinetic energy of non-interacting electrons, means that, as I said before, it has densities which are sum over single particle wave function squared. At fixed electron number, the variation principle, which we had stated before, implies that the variation of EV of n minus constraint of the nuclear number means a Lagrange parameter times the integral over the density minus n should be 0. And if you just put these things to the left and the right side and put in for EV what is on the top, I see that the variation of the exchange of the total energy functional with respect to the density means mu equals the derivative of the kinetic energy functional plus the effective potential, where the effective potential is the functional derivative of the top. That means the Coulomb potential of nuclei, the Hartree potential, and the functional derivative of exchange and correlation. Because Ts is the function of non-interacting particles, we effectively restrict the allowed density to those that can be written down as n being the sum over phi squared. And that implies that I can put this in, that nabla squared, that nabla square plus effective potential times phi equals a single particle energy times phi, where the effective potential depends on the density that we are looking for. This is what's called the Kohn-Sham equation. The only unclear situation here is, again, we don't know exc of n, and that means we also don't know really the functional derivative. Again, this is where we need approximations. Now, the power or the quality of density functional theory has been shown in the very first calculations with the so-called local density approximation. We know that exc is a universal functional in n of r, and they are independent of the special system. And there has been, in fact, even before density function theory, there has been quite some knowledge about exc. Now you can write down exc as a sum over, as an integral over the exchange correlation energy per particle of a given density times n of r, integrated over r. So this is exact. And then you can make a, say, series expansion where you say, I make an expansion around constant densities and then correction terms. This exc LDA or exc gellium, gellium means a constant electron density, has been known before. Wigner has shown already in 1938 that exc of a constant electron density for small densities behaves as this dashed line here. And Gell-Mann and Brückner, with some more sophisticated many-body theory, have shown in 57 that the high density limit looks like this. Now, all the realistic systems are in between. But this is, in fact, what is called the local density approximation, namely replacing epsilon xc of n by this function epsilon xc gellium. As I said, the region which is important is here, and we didn't know actually what should be there. And here comes the work by Chapperley and Alder by Quantum Monte Carlo in 1980, and they have shown from Quantum Monte Carlo how this should work, and surprisingly, very smoothly, it simply connects the Wigner and the Gell-Mann-Brückner terms. So we now know exc gellium, and so for this simple approximation, we have the correct answer. In general, we don't know, and approximate functionals have been very successful. The LDA is still sometimes used, but there are problems. What is missing, for example, is certain bonding situations are not described well in these simple treatments. Van der Waals interactions are missing. Hydrogen bonding is not treated well. Certain covalent bonds are not treated well. Highly correlated, that means localized bonding situations, are not treated well, and excited states are also not treated appropriately. As I said, we don't really know about the accuracy and the limits of the different functionals. Still, Perdue has formulated what I call this Perdue's dream. He calls it a Jacob's ladder, which in fact is from the first or the Old Testament, a dream of Jacob, where he sees angels going up a ladder towards heaven. And so the idea is that the first step, the first level, is the local density approximation we have just seen. The second one is then the generalized gradient approximation. So the point is that I do a dash here because this is the approximation of the local density. There should be no dash here in the general gradient approximation because it's not really that the gradient is generalized, but the gradient approximation. So if you would do this sum which I had on the previous one, which I said you have the local density approximation, then you have higher order terms in the gradient of the density. If you would do this, say, naively, you would see that the first correction term would not really give you a better description than the first one. There are some misleading terms in it, and so what Purdue has done is generalizing the gradient approximation. The third level is getting more information in, and that is called the meta-GGA. In the meta-GGA, you're not only including the gradient of the density, but you also include the Kohn-Sham kinetic energy density. And the most accurate meta-GGA which now exists is again derived by Purdue, is SCAN, which is a functional which fulfills all the exact conditions which we know about the correct exchange correlation functional, all the parameters which in fact a meta-GGA could fulfill. An even higher level would be including also occupied orbitals. So you're moving a little bit away from the concept of density function theory that you now include also and allow also orbitals, but to some extent you were away from it already when we started in dealing with the kinetic energy functional, which we also evaluate as a functional with orbitals. So in hybrids, V3-lib, PBE0 or HSE are the popular ones. One also includes orbitals. That means one includes also what is called the exact exchange from Hartree-Fock with a certain fraction. And the highest level then is the random phase approximation, RPA, for correlation, and for the exchange one uses really the Hartree-Fock exchange expression. So here we are not only having occupied but also unoccupied orbitals. And of course you see that going higher and higher in this ladder means that the treatment is getting more and more complex. But we can do all this. We can do improved functionals. They are not always improved. I mean, in principle, they are better because they have more flexibility, but it's not 100% clear if they work better in all cases. The favorite, if you really want a comparison, being more or less sure that, or not sure, if you want to say some confidence that you're right, would be in going to level 5. Because functionals of level 1 and 2 suffer clearly from severe self-interaction errors. The electron sees itself, which is certainly wrong. Functionals of level 1, 2, 3, and 4 are lacking the long-range van der Waals tails. You could add them. Alex Tkachenko and colleagues and other people and Grimme have added basically the tails to it. That works. It's somewhat a pragmatic solution. But with level 5, we are at a situation now that we have a validation possibility. We can, in fact, estimate our errors. Still, I would say it's not the exact treatment. If you really want an exact treatment, it would be good if coupled cluster theory would be possible. Let me conclude this part dealing with concepts of the theory by this picture of Walter Kohn, which shows him at West Beach, Santa Barbara. That is where he lived at age 75. He died, in fact, in April 2016 at an age of 93. What you see here is the success stories of the picture showing the success story of density function theory. In red, these are the number of articles, the citations, articles which cite density function theory. And you see this clearly low starting and then exponential growth. And in blue, and that is the unusual thing, is that even in patents, the term density function theory is shown, is used to somewhat prove that the pattern is right. That it was realized that this is a good theory was here when Walter Kohn got the Nobel Prize. I started somewhat early in 1980, so basically nothing is seen here in 1990, even less was there in 1980. And of course, the theory started with Walter Kohn's work in 1964. This is basically where his left hand is on this picture. And let me now continue and show you what convinced me that this is a good theory, although in 1980 very few people were doing anything on that. Let me now demonstrate for some examples which type of information can be obtained using DFT. I decided to show some historical examples as they demonstrate a key issue of basic research, namely the importance for posing the question cleverly. Despite the age of these examples, I would say that these are still the best ones. It is your chance for doing better. Before 1980, systematic high-quality DFT calculations were not possible, partly due to the lack of efficient and reliable algorithms and partly due to the lack of computational power. Therefore, it was often not understood how the electron density is distributed in the crystal and how a solid is stabilized. It was, for example, not clear why silicon does exist in the diamond structure or why silver has an FCC structure. The main advantage of parameter-free self-consistent DFT calculations is that the results can be analyzed in detail. That is, we can understand which mechanisms are essential for a certain material's property and which are not. For example, in order to find the lowest energy structure of a solid, the energy will be studied as function of the lattice geometry. Here is a figure from what I consider to be the first convincing example demonstrating what type of problems can be tackled by density functional theory calculations. These are calculations performed in the group of Marvin Cohen in Berkeley. The figure shows the total energy for silicon as a function of the volume per atom, where the volume, that is the x-axis, was normalized such that 1 is that of the experimentally known result for silicon in the diamond structure. The results show clearly that the lowest energy of all considered structures is indeed found for the diamond structure, and the minimum of the theoretical curve is very close to the experimental result. The figure further reveals that there is a phase transition that eventually brings the system into the beta-tin structure when the volume is reduced. The slope of the common tangent of the two curves for the beta-tin and the diamond structure gives the pressure at which the phase transition sets in. This common tangent is called the Gibbs construction. Such calculations can predict and explain why solids behave as they do, and new materials of hitherto unknown structures or composition can be investigated as well. The approximations of this study are listed here. They are still very common also in today's research. The authors continued this study by analyzing the nature of bonding, but before showing such figure, I like to mention that there was another study that belonged to this headline, the first convincing DFT calculations, and this was even 2 years earlier than the Marvin Cohen result. I will get to this in a moment. There is one more result from the Cohen group, which I'd like to share with you, the valence electron density of semiconductors, comparing germanium, gallium arsenide, zinc selenide. You see these atoms here in the periodic table. You just go to the left and right from germanium. And very clearly, one sees that for germanium, the bond is covalent. The electron density is very nicely in the middle between the atoms. In gallium arsenide, it's still largely covalent, and in zinc selenide, it's already largely ionic. Here is the already mentioned work by Moruzzi, Janak, and Williams. These authors looked at many metallic solids. The approximations were similar to the previous one, with one important difference. These are all electron calculations. The previous study was a pseudopotential calculation. So this is all electron like in FHI-aims. But back then, this all electron treatment required the muffin-tin approximation. That is, making the effective potential spherical around the atoms. This approximation is no longer necessary today. Moruzzi et al. Calculated quantitative results and trends. Lattice constant, cohesive energy, bulk modulus, density of states, band structure, susceptibility enhancement, spin polarization. And all this for many atoms already in 1978. Here is another example which demonstrates how density function theory calculations can be used, how they can teach us about geology, about our Earth. That's information that we cannot get otherwise. Safe knowledge about the Earth only exists about the crust and the upper mantle. However, it is interesting and indeed important to know more about the central region of our planet, as this, for example, contains information about the origin, the development, and the future of our Earth. One aspect here also is the question, what determines the Earth's magnetic field and its fluctuations and changes? The structure of the Earth is known from measurements of the propagation and time delays and phase differences of earthquake waves, as these are reflected when the composition of the aggregate state in the Earth change. The inner core of the Earth is most likely solid. And then we have the outer core, which is liquid. We know the depth, and we also know quite accurately the pressure, as this can be estimated from the depths, and that tells us about phase boundaries between the solid and the liquid core. The depth is noted here on the y-axis and the pressure noted on the x-axis. The material down here is mostly iron, probably with some little fraction of oxygen, sulfur, selenium and carbon. Unclear, however, is the temperature at this place. In fact, we don't know at what temperature does iron melt when it's put under such high pressure of 330 gigapascal. And we have no idea how such melt may behave. What is the local structure? What is the viscosity of the melt under such extreme conditions? The problem is that such pressures can hardly be reached in the laboratory. With a diamond anvil cell, one gets somewhat close to 200 gigapascal, but not to 330 gigapascal. Now, density functional theory calculations by Alfei et al. Have shown that the melting temperature of iron at 330 gigapascal is 6,607 Kelvin. You see this here on the figure. This shows you the calculated phase transition curve, the melting curve of iron. And at 330 gigapascal, this temperature is 6,670. This is the temperature at this border line. So this is, I think, what makes a good scientist. Using a method for an unexpected situation. And in simple words, one could say, in this case, density function theory was used as a thermometer to determine the temperature at an inaccessible place. Beyond calculating the melting curve, the authors also studied the viscosity of the material. The previously existing experimental estimates differed by many orders of magnitude. The DFT work showed that liquid iron in the outer core should have a local coordination similar to that of the HPC structure, and the viscosity is only by a factor of 10 higher than that of liquid iron at standard on-Earth pressure conditions. This is actually on the lowest side of the previous experimental estimates. Of course, there are also some uncertainties in the theoretical results. These uncertainties arise because a somewhat small supercell was used, the exchange correlation functional was treated approximately, and the authors studied pure iron, that is, without oxygen, sulfur, and so on fractions. That must be there as well. They have later, in fact, refined these calculations. Altogether, the uncertainty of the calculated viscosity may be a factor of 3, but this is still much lower and uncertainty than that of the experimental studies. It is now clear that in the outer core, local circulations and turbulent convection will occur. At most of the previous experimental estimates, that was not possible because the viscosity wasn't right. Let me finish this introduction and overview with a summary and outlook, which tells that interacting electrons determine the properties and the function of real materials. And interacting electrons have an enormous amount of driving an enormous amount of different mechanisms. Here is a quote from John Purdue. Correlated wave function theory provides the right answer for the right reason, but at a high computational price for systems of many electrons. Kohn-Sham density function theory employs a simpler, non-interacting or Coulomb uncorrelated wave function, but includes a density functional for the exchange correlation energy that is exact in principle, but requires improvable approximation in practice. It often provides almost the right answer for almost the right reason at almost the right price for real atoms, molecules, and materials. I definitely agree with this statement by John, though I hesitate a little bit with the words the exchange correlation energy that is exact in principle. That is, I don't really see that this functional really exists beyond the algorithms that I had discussed earlier in my talk. In addition to this question, there are still important arenas for future theoretical work. Non-adiabatic effects, dissipation, transport of electrons, of ions of heat, thermodynamic phase transitions, for example, melting, modeling the kinetics, for example, in catalysis or crystal growth, self-assembly and self-organization in realistic environments, treating molecules in clusters, for example, biomolecules in solvents and electrochemistry, fuel cells, external fields, looking at correlated systems, that means, for example, F-electron chemistry, big data analytics, statistical learning, compressed sensing, and so on. There has been and is being made presently a lot of progress in all these areas, but there's still a lot of work to do. Quite a number of these points will be discussed during this course. In very simple ways, all these challenges can be summarized by two statements. Find ways to control the exchange correlation approximation and develop methods for bridging length and timescales. So this is the end of my talk, and I'm happy to hear your remarks and questions.